causes a lily pad in the lake to drift at a constant speed of 1.37 meters per second. As the lily pad passes by a frog, the frog waits until it is a certain distance away and leaps towards it. If the frog leaps at 3.70 meters per second at an angle of 24 degrees from the horizontal, how far away from the frog must the lily pad have been in order for the frog to land on it? Okay, so the first thing we want to do with this question is draw a picture. So I'm going to draw an x and y axis here. So I have my vertical, my y-axis, and my horizontal x-axis. And I have two objects here. I have a lily pad and I have a frog. So the current causes the lily pad to drift at a constant speed of 1.37 meters per second. The lily pad passes by the frog and the frog waits until it's a certain distance away from it and then leaps towards it. Okay, so let's say this is the lily pad right here. So I'll put a little L there to show that that's the lily pad. And the lily pad is traveling away from the frog. So I'm going to say the frog is over here. So that's my frog. My frog is waiting until the lily pad is a certain distance away and then it's going to jump on it. So the lily pad is traveling in a straight line. So it's moving. I'm going to say this is the velocity of the lily pad is equal to 1.37 meters per second. Okay, so now we have the frog, and the frog is waiting until the lily pad is a certain distance away, and then it's deciding to jump. So the frog is going to jump with an initial velocity of 3.7 meters per second at an angle of 24 degrees above the horizontal. And the frog jumps, and so it becomes this projectile. It goes up, and then eventually lands, and it wants to land right on top of the lily pad. Okay, so this is where it's going to land. And it wants to know how far away from the frog should the lily pad have been in order for the frog to land on it. So we're looking for that initial distance between the frog and the lily pad. So really this value right here. We're looking for that value. So I can call that whatever variable I want. I'm going to just call that variable x. Okay, so I'm calling that x. All right. And I'm just going to put in my arrow for the lily pad so I can see. This is my lily pad vector. It's moving to the right, and it says velocity of the lily pad is 1.37 meters per second, so that's good. So what we want is for the frog to land on top of the lily pad. So what we're going to do in this question is we're going to start with the object that has the simpler motion. Okay, so we look at the frog's motion, it's a projectile. The lily pad's motion is just in a straight line, it's one-dimensional, it's just going to the right. So we're going to start with that lily pad because it has the simpler motion. Okay, so I'm going to write out lily pad here. And what I want to do is find an expression for the final position of the lily pad. Okay, so I'm going to find the final x position and the final y position. So the final x position first is what we're going to look for. Well, what do we know about the lily pad? We know its initial x position, which we called x over here. So that's its initial position. We know its velocity of the lily pad, which is equal to 1.37 meters per second. And we know that it's drifting at a constant speed, which means it is not accelerating. So its acceleration is 0 meters per second squared. So let's find its final x position. So we have this equation, S final equals S initial plus V initial delta t plus 1/2 a delta t squared. So because a, acceleration, is 0, this whole term goes to 0. So my SF, I'm using XF to describe the final x position, equals the initial position, which we said was x, plus the initial velocity over here is 1.37 times the time. Now we don't know the time, so we're going to keep this expression the way it is. We can't actually solve for XF, but at least we have an expression for it. Okay, so now that we're finished with the more simpler object, we're going to go to the more complicated one, which is the object that is moving as a projectile, and that would be the frog. Okay, so we're going to move on to the frog over here. Okay, now because the frog is moving as a projectile, we're going to have to separate the x and the y components for all of these variables. So we're going to draw a table. Okay, this is what we do for all projectiles. We draw this table so that we can separate the x and y components of each of the kinematic variables. So I have initial position, final position, initial velocity, and acceleration. Okay, so the initial position of the frog is right here, and the final position of the frog is right here. Okay, so initially the frog is at the origin, so its x and y components are both 0. At the end, the final position of the frog is on top of the lily pad. So what is the final position of the lily pad? Well, we just found it over here. Because we want the frog to land on top of the lily pad, we want it to have the same final position as the lily pad does. So the lily pad's final x position is x plus 1.37 delta t. And what is the lily pad's final y position? Well, the lily pad, we're assuming, doesn't have a thickness to it. It's really thin, so we're going to assume it's just right on the x-axis here. So that means its final y position is 0. So the frog is landing on the lily pad, so its final y position is also 0. Okay, so what about the initial velocity of the frog? We know it's 3.7 meters per second at an angle of 24 degrees above the horizontal. So we're going to have to decompose this vector into an x component and a y component over here. Okay, so notice the x component is the adjacent side to the 24 degrees, so we're going to use cos. So it would be 3.7 cos of 24 degrees. And the y component is the opposite side of the 24 degrees, so we're going to use sine. So it would be 3.7 sine of 24 degrees. Okay, now the acceleration. For a projectile, the acceleration in the x direction is always going to be 0. And since we're close to the surface of the Earth, the y component of the acceleration is 9.8 meters per second squared, pointing downwards. And since it's pointing downwards, we have to remember to put a negative sign there, because up is positive, down is negative. Okay, the next thing we're going to do is pick which column has the most information, and we're going to use that column to solve for time. Okay, so take a look at the x column and the y column. Which one has more information? So that would be the y. So I'm going to write y direction, so I'm showing you which variables I'm dealing with here. I'm looking at all the numbers only in the y column, and I'm ignoring the numbers in the x column. I'm going to solve for time. Well, I know S initial, S final, V initial, and A. So to solve for time, I'm going to use the first kinematics equation, which is S final equals S initial plus V initial delta t plus 1/2 A delta t squared. So let's plug in everything we know. S final is 0, S initial is 0, plus V initial is 3.7 sine 24, delta t plus 1/2, A is negative 9.8, delta t squared. So I'm just going to type this in my calculator to simplify it. So 3.7 sine of 24 is 1.504. I'm going to keep some extra digits. 9.3 delta t minus, so 1/2 times negative 9.8 is negative 4.9 delta t squared. So I'm trying to solve for delta t. I'm going to factor out the delta t here. So I have delta t. I'm going to factor it out. So I have 1.50493 minus 4.9 delta t. So I get delta t is equal to 0, and delta t is equal to 1.50493 divided by 4.9. So I'm going to type that into my calculator, and I get 0.30713 seconds. Okay, so now I found out the time. This is the time it takes for the frog to land on the lily pad. Now the question is asking, how far away from the frog must the lily pad have been? So it's looking for that X that's in this X right here, that's in my drawing. So I want to know, how far should the frog be from the lily pad when the frog decides to jump, so that it will land on the lily pad. Okay, so I'm looking for that X. So what I'm going to do is move on to the Y direction. So if I look, sorry, move on to the X direction. So if I look at the X direction now, I'm looking to solve for this X that's over here. Okay, so I still have the same variables as before, S initial, S final, V initial, and A, and this time I also know delta T. So I'm going to use the same kinematics equation that has all those variables, S final equals S initial, plus V initial delta T, plus 1/2 A delta T squared, and I'm going to plug in everything that I know. So my S final is X plus 1.37 delta T equals, my S initial is 0, plus my V initial is 3.7 cos 24. My delta T is what I just found from the last step, 0.30713, plus 1/2, my A is 0, and then my delta T is still 0.30713, and that's squared. Okay, so now this delta T is also the same value that I found before, the 0.30713. So I can plug that in, and then you can notice that this is left as the only variable now. Okay, so I'm going to simplify what I have so far. I have X plus 1.37 times 0.30713 is equal to, and on the right side I'm just going to type everything up. So 1/2 times 0 times anything is just going to be 0, so this whole thing goes away, goes to 0. So now I'm just typing 3.7 cos 24 times the 0.30713, and I get 1.03813. And now I'm still solving for this X, so I'm going to bring the 1.37 times 0.30713 to the other side, so I get 1.03813 minus 1.37 times 0.30713. I'm going to just type that in to my calculator, and I get my X value is equal to 0.617. Okay, so if I look back at the original question, it asks how far away should the frog be from the lily pad before it jumps. I can see all the values we were given have three significant figures, so my answer should also have three significant figures. So 0.617 is correct. We just want to make sure we include the units, so it would be meters. And that is my final answer. Okay, I hope that helped. Thanks for watching.